What specific problem does the GenRM method aim to solve, and why is it necessary to improve upon existing verification strategies for LLM-generated solutions?
The GenRM method aims to solve the problem of inaccurate verification of solutions generated by large language models, LLMs, particularly in reasoning tasks where a single mistake can invalidate the entire solution. Existing verification strategies, such as discriminative reward models, RMs, do not leverage the text generation capabilities of LLMs, which limits their effectiveness in accurately assessing solution correctness. By framing verification as next token prediction, GenRM utilizes the inherent strengths of LLMs, such as chain of thought reasoning and unified training, for solution generation and verification, leading to improved performance. The necessity of GenRM arises from its ability to enhance verification accuracy through methods like majority voting and COT reasoning, which traditional approaches fail to implement effectively. Overall, GenRM demonstrates significant improvements over existing methods, making it essential for advancing the reasoning capabilities of LLMs.
How does the GenRM algorithm work? Illustrate the methodology step by step, detailing how it transitions from the traditional discriminative verifiers to this new generative approach.
The GenRM algorithm transitions from traditional discriminative verifiers to a generative approach by leveraging next token prediction for solution verification. First, instead of assigning a numerical score to candidate solutions, as done in discriminative reward models, RMs, GenRM predicts the correctness of a solution using a single token, either yes or no, based on the context of the problem and the proposed solution. This is achieved by maximizing the log probability of the yes token for correct solutions and the no token for incorrect ones, effectively integrating the verification task into the generative capabilities of the language model. Furthermore, GenRM incorporates chain of thought, COT reasoning, by generating intermediate rationales before making a correctness decision, which enhances its ability to detect subtle reasoning errors. Finally, the methodology includes majority voting, where multiple COT rationales are sampled to average the correctness scores, thereby improving the overall accuracy of the verification process.
Can you provide a simple yet illustrative example of how GenRM evaluates a candidate solution? Walk through the main algorithmic steps using a hypothetical math problem.
To evaluate a candidate solution using GenRM, consider a hypothetical math problem. What is 5 plus 3? The process begins with the LLM generating multiple candidate solutions, such as 8 and 6. For each candidate, GenRM employs next token prediction by prompting the model with "Is the answer correct?" and calculating the probability of the token yes, given the context of the problem and the candidate solution. For instance, if the model predicts a high probability for yes for the candidate 8, it indicates confidence in its correctness. Additionally, GenRM can utilize chain of thought, COT reasoning by generating intermediate rationales before making the final correctness prediction, which helps identify any subtle reasoning errors. Finally, if multiple COT rationales are generated, majority voting can be applied to average the correctness scores, enhancing the overall accuracy of the evaluation.
What are the practical benefits of using GenRM compared to traditional discriminative RMs, and how does its performance scale with model capacity and dataset size?
The practical benefits of using GenRM over traditional discriminative RMs include its ability to leverage the text generation capabilities of LLMs, allowing for unified training of solution generation and verification, which enhances overall performance. GenRM utilizes next token prediction to represent solution correctness as the probability of generating a yes or no token, which improves the model's calibration and reduces misclassification errors. Additionally, GenRM COT, which incorporates chain of thought reasoning and majority voting, significantly boosts verification accuracy, particularly in complex reasoning tasks, outperforming both discriminative RMs and LLM as a judge approaches. Performance scales positively with model capacity, as larger models can learn more effectively from the same data, and Gen-RM COT benefits from increased dataset size and the number of rationales per solution, leading to improved accuracy and robustness against noise in synthetic rationales. Overall, Gen-RM demonstrates superior scalability and adaptability in reasoning tasks compared to traditional methods.
How was Gen-RM validated in the experiments? Describe the experimental design, datasets used, and the benchmarks that were employed to evaluate its performance.
Gen-RM was validated through a series of experiments focused on reasoning tasks, specifically last letter concatenation, word sorting, and GSM-8K, which are designed to assess the model's reasoning capabilities. The experimental design involved comparing Gen-RM against standard verification approaches, including discriminative reward models, RMs, self-consistency, and LLM as a judge, to evaluate its effectiveness in selecting correct solutions from multiple candidates. The datasets used included a mixture of correct and incorrect solutions for training, with a balanced dataset for the verification tasks, and the performance was primarily measured using the best of n metric, which evaluates the percentage of problems solved correctly. Additionally, the experiments incorporated majority voting for Gen-RM COT, where multiple chain-of-thought rationales were generated to enhance verification accuracy. The results demonstrated that Gen-RM outperformed the baseline methods across all tasks, indicating its superior capability in reasoning and verification.
What specific results were achieved with the Gen-RM method on tasks like GSM-8K and last letter concatenation? How do these results compare with existing methods, and what do they imply about the effectiveness of Gen-RM?
The Gen-RM method achieved significant improvements on tasks such as GSM-8K and last letter concatenation. Specifically, on GSM-8K, the Gen-RM COT model demonstrated a 20% increase in the number of problems solved, improving from 73% to 92.8%, which surpassed the performance of both GPT-4 and Gemini 1.5 Pro. In the last letter concatenation task, Gen-RM outperformed standard discriminative reward models, LLM as a judge, and self-consistency approaches, indicating its superior capability in reasoning tasks. Additionally, the use of majority voting with Gen-RM COT further enhanced performance, nearly matching that of an Oracle verifier on algorithmic reasoning tasks. These results imply that Gen-RM effectively leverages next token prediction and chain-of-thought reasoning, leading to a more robust verification process compared to existing methods.
Discuss any limitations or drawbacks of Gen-RM highlighted in the paper. Are there specific scenarios where this approach may not perform well?
The paper highlights several limitations of the Gen-RM approach. One significant drawback is that while Gen-RM COT can outperform standard verifiers, it still relies on the quality of the generated rationales. If the synthetic rationales are of poor quality, the performance may suffer, as evidenced by the results showing a notable difference in accuracy when using reference-guided grading versus random generation. Additionally, Gen-RM's performance may not be optimal in scenarios where the reasoning required is particularly complex or nuanced, as it may miss subtle errors that a more sophisticated verifier could catch. Furthermore, the reliance on majority voting for COT rationales can introduce variability in performance, especially if the generated rationales contain conflicting information. Lastly, the paper suggests that while Gen-RM scales well with data and model size, there may be diminishing returns in performance improvements as the model size increases, indicating potential limits to its scalability.
What future directions do the authors suggest for research based on their findings with Gen-RM, and how could this work be built upon?
The authors suggest several future research directions based on their findings with Gen-RM. One potential direction is to further explore the integration of generative verifiers with larger datasets and model capacities, as the results indicate that Gen-RM's performance scales positively with these factors. Additionally, they highlight the importance of improving the quality of synthetic rationales, suggesting that reference-guided grading could be further refined to enhance the accuracy of generated rationales. Another avenue for future work could involve investigating the application of GenRM in more complex reasoning tasks beyond those tested, potentially expanding its utility in various domains. Lastly, the authors imply that the unification of solution generation and verification could be leveraged to develop more sophisticated models that can better understand and generate correct solutions, thus enhancing overall reasoning capabilities.